Okay, so we missed few things there. I was recording and the recording was stopped. Anyway, I will just continue from the last video. So we were talking about this exchange current density. So now you can see over here that there are certain part of this last equation which we see over page. We were talking about this over here, that is the exchange current density, and this exchange current density is basically incorporated from this condition over here, which is when E is equal to E equilibrium and there is no overpotential. So you can see that this term over here, if you exclude area from this term, then you actually get the exchange current density. So anyway, now we move over here. We have two limiting forms of the Butler Volmer equation that we will consider over here. One is the small overpotential and the other one is the large overpotential. Now in case of small overpotential, we are talking about overpotential smaller than this 8 millivolt divided by the number of electrons, and if this is the situation, then we can consider that we can write the exponential part of the equation in its linearized form over here. So under small amplitude we have a certain plot over here, that is, it will give us a linear relation between the current and the overpotential, and we will get a very important term over here. So this is the ohmic behavior of heterogeneous transfer of electron at low overpotentials. So considering the last equation that we derived, that is the simple equation, that in the simple form of the equation, we can write this equation, that is we can linearize this part of the equation over here by using this assumption and write it in this linearized form which you see over here. Now if this is simplified, if this equation is simplified, then we get the relation between the net current and the exchange current, number of electrons and overpotential. So by analogy with the Ohm's law, we get this admittance over here, and then we get a very important parameter which is the impedance or Faradic resistance. Now we can actually see over here that this admittance is the slope of this line, and this line is actually passing through the origin over here, so it is a linear form and then it is passing through the origin. So this admittance and the impedance both are very important parameter, and admittance tell us that if it has a high value, then we are looking at faster heterogeneous electron transfer, and vice versa, that is, for low admittance the heterogeneous electron transfer will be slow. Remember that it is under the condition that the overpotential should be lower than 8 millivolt per electron. Now we know that near the equilibrium potential, an electrochemical reaction gives a linear current versus potential curve, which we already shown, which is given over here. This is a linear curve and this has zero current intercept, that is, it is passing through the origin, and this slope will give the transfer admittance. So next we have the high overpotential situation, in which the overpotential value is higher than 120 millivolt per number of electron, and assumption that one of the reaction rate is negligible. So we can write that this is the net current, which can be written in the logarithmic form like this, and this can be plotted to give us a very important plot, which is the Tafel plot. So we can also take the derivative of this, since it is constant, so it will get to 0, and then we get this equation over here. Anyway, so if we plot this here, so we get a linear part and then we get a curved part. This linear part is called the Tafel region. So you can say that from here to here it is the Tafel region, and this one over here, that is the curved part, this is the ohmic region. So if you actually extrapolate this linear part, so what you get is this log of the exchange current, and then you have this. So basically you are getting the exchange current density from this plot, and then you are getting this value for the transfer coefficient. So both of these values are very important. So you can see that transfer coefficients and the exchange current density can be determined here. So Eyring equation is, as you know, that it actually incorporates all the effects and all the values of the overpotential, larger and smaller, and all the values. So if we consider that and we plot, we see that we actually get a very interesting plot over here. And basically this is a current potential curve, and we have included here positive potentials, then we have included the negative potential, and then we have this cathodic current, and then we have this anodic current. And you can see over here that we are looking at overpotentials which are related to the cathodic processes, and then we have the overpotential related to the anodic processes, and then we have these exponential forms which is coming from the cathodic current for the cathodic process and the anodic current from the anodic process. So for the cathode we are looking for reductions, and on the anode we are looking at the oxidation. Then we have this net current which is present over here, and it is passing again through the origin, and since it is passing through the origin, so it actually conveys certain thing. Although it is passing through the origin, but we must remember that this part doesn't mean that here the electric field is not equal to 0, and then it gives other informations also. So this plot is quite important, and actually in this plot we look at the Butler Volmer kinetics together with the Tafel relation. So you can see that again there is a linear part, there is a linear part over here, and then we have this curved part over here which is actually going like this. So all of these are included, and we are plotting overpotential versus the current densities. Now these type of plots have practical implications. That is, actually it can give us information about certain processes. For example, if you are looking to control corrosions, for example, like in this paper, that which is information is given over here. So people, these scientists tried to study and control the corrosion with the help of this type of study, in which the current density and overpotentials are plotted, and we have got the plot that we just saw on the last slide. So if you study in detail, you will see that how the information related to the oxidation and reduction processes occurring can help to control a certain surface process. Because if you are able to control oxidation or reduction, it means that you will be able to control the corrosion. So that's all for this lecture, and we will start again with some new topic.